In this segment, we're going to look at how to use local definitions in practice and how to do calculations using them. Okay, let's get started, and we'll look at an example and do a bit of live coding of a solution for that using local definitions. Here's the problem. Given three integers, tell me the maximum and how many times that maximum occurs. So if we apply the function to the numbers 555, we get a pair in our answer. I'll talk about pairs and related types a bit later on, but for now we'll use them without explanation. The maximum is 5 and it occurs 3 times. If we apply the function to 5, 0 and 5, the maximum is 5, it occurs twice. If we apply the function to 5, 0 and 4, the answer is 5 and it occurs once. So the answer is the pair 5 and 1. Now, how can we go about writing a function that does that calculation? Here we are inside an editor, and I've started to write the definition. I've specified the type and I've written the left-hand side. So now I'm going to write the right-hand side of this definition, which is the equation. So I'm going to say the answer is got two halves, it's in a pair, and it's going to be the max and how many times it occurs. And I'm going to define both of those things using a where clause. So I'm going to say the max equals whatever and occurs equals. Now, how do we go about calculating the max? Well, we've talked about this before. What we can do is take the maximum of max x, y and z. So we do that. There we've got the maximum. Now, how can we go about counting how many times that occurs? What we need to do, we need to check for each of x and y whether it's equal to the max. If it is equal to the max, we count that as 1. If it's not equal to the max, we count that as 0, and we add them all together. So what I'm going to do is define a function, eq, that does that for us. Eq we can apply to x and to y and to z. And this, when we apply it, we apply it to w, say, it will check whether w is equal to the max. And if w equals the max, then the answer is 1. Otherwise, the answer is 0. So here we've got our definition. Let's save the file and let's reload it in here. And let's try it out. What happens if we do flights 5, 5 and 5? We get 5, 5 and 4, we get 5,2, 5, 2 and 3, we get 5,1. So we're getting the answers we would expect. Let's just go back to the definition and see what we've done again. So we're saying the answer is got these built up of these two numbers, the max, which we calculate by applying the binary max function twice, and then we work out how many times it occurs by using this eq function that gives the answer 0 except if its argument is equal to the max. And so we'll only score 1 for each of these if that number x or the number y or number z is equal to the max. And so that gives us, you can see here we've used our local definitions to give a constant like the max or a function like eq. And note that eq uses the max in its definition. So we can use one locally defined thing inside the definition of another. So that just gives us one more example of using local definitions. Let's go back to the presentation now. So I've talked about the examples we've seen are in a where clause. So where gives a definition that's local to an equation, local to a definition. We typically use it when we define functions in a module, and given that's where we do most of our work in Haskell, we'll find that most of the time we're using wheres. But you can use let, and let gives us something that is local to an expression. So we can use it in an expression we give to GHC to evaluate. So for example, we can write something like let s equal 3 plus 4 plus 5 divided by 2 in this large square root. And this is the formula you see at the top of the slide. It's the formula for the area of a triangle. And here you can see at the bottom, I've used that and I've got the answer 6. Let's conclude with a calculation. We've got a simple function here that takes two numbers and gives us back the sum of their squares. And the way it does that is to use, in a local definition, does the square of each of the numbers separately, and then at the top level we add those two results together. And I'd just like to show you in a hand calculation how we can use local definitions just as we do ordinary definitions in doing a calculation, writing out by hand the evaluation of this function. There's a second example at the bottom of the slide which I'll leave to you as an example for you to do yourselves. But let's get going with the hand evaluation. And here you are. You can see that we have the function. I've just cut and pasted into the screen here. And let's do the example of sum SQ of 4 and 7. Now that rewrites to square n plus square m, and we have to, inside our local definition, work out each of these. Square n is n times n, where n is 4, so that is 4 times 4, which evaluates to 16. Square of m is m times n, which is 7 times 7, which is 49. And so then we can say that square of n plus square of m is 16 plus 49, which rewrites to 65. And so we get our answer. Well, I've shown in this indented area here, this is where we do the local calculation. So just as we're able to do local definitions, we do local calculation like that. So what we've seen here is a local calculation using that where clause. And as I say, I leave it to you to do a local calculation using of this expression here, which again is involving a calculation of the area of a triangle. Okay, that's it for where and let definitions. As I said earlier on, these local definitions get used very heavily in defining functions, and typically we're using where more heavily than let. So it's something that is part of our toolkit, and particularly our toolkit for breaking more complicated problems down into a number of simpler problems. And you can see that a very simple example of that here. We need the sum of squares of n and m. Well, let's separate that down and say we'll sum the square of n and the square of m, and then separately we work out what each of those squares is. That's a very simple breakdown, but we use that kind of divide and conquer, it's called, throughout function definitions that we write in Haskell.